Okay, I'm going to show you now how to get a displacement graph from a velocity time graph. I'll also show you how to get an acceleration graph, but that part's dead easy. Okay, so I have an example here. I got this worksheet from physics.info, and right here we have a velocity time graph, and we're going to plot a displacement time graph exactly above it. First thing I want to do is line things up. So you can see from the velocity time graph that we have different stages of velocity. So I'm just going to draw a light line so that I know where one stage ends and the next one begins. Okay. Now the key concept is this, and it actually has to do with the fundamental theorem of calculus. The displacement is equal to the area under the velocity time graph. Now that should make sense to you because we define velocity as displacement divided by time. Now what that means is that displacement is equal to velocity times time. So if you have a graph where over here you have velocity and here you have time, then when you look at one portion of it, if I draw a rectangle there, under one portion of it, that's delta t, the time interval, that's the velocity, and the area of that rectangle is equal to velocity times time over that time interval. So that's the displacement, that's how far the object will move in that time interval. The entire curve can be thought of as a whole bunch of rectangles. And if we were to add up the area of all those rectangles, that would approximate the area under the curve, or the total displacement, from our velocity time graph. It would approximate it. But if I had an infinite number of rectangles that were infinitely small, we're no longer approximating. It would actually be the displacement, or the area under the velocity time graph. So that's sort of a justification for why this should work. Okay, so the first area of interest actually is when our velocity starts off at 4 meters per second and makes its way down to 0. All this time our object is moving forward because we have a positive velocity. That positive velocity is decreasing as we go. The area up to that point is the area under this triangle. Now this triangle goes out a distance of 4, and it goes up a distance of 4. So this square has an area of 4 times 4, which is 16, which means the triangle has an area of 8, exactly half of that. So what that means is by the time I get to here, my displacement is 8. Now each of these is 5, that's 10, so 8 is right about here. My velocity starts out fast, and it gets slower and slower. So the steepness of my displacement time graph starts out steep and gets flatter and flatter and flatter. So right now the area here is equal to the height here. So we have an increasing height which tracks our increasing area as we make our way from left to right. The area under the curve is negative. So as we add negative area, we're taking away from our height. So as we make our way up to, and that's at 8, we have to subtract 4 times 4 divided by 2, or 8. So this curve is going to make its way back down. So by the time we get to here, the total area under the curve is 0. We have a positive area of 8, and then below the line we have a negative area of 8. They've canceled each other out by now, and we're back down to 0. Okay, this next phase is really easy. Right here I've got a delta t of 4. I'm going over 4. And all of that is exactly 4 down. So my area here is 4 times 4, which is 16. It's all negative. So my displacement from here to here is negative 16. So we've got 5, 10, 15, and just a little bit more. That's negative 16. Now, what kind of shape do I expect this motion to have here? My velocity is constant. Constant velocity corresponds with a straight line on a displacement time graph, because your displacement is changing at a constant rate. During this segment here, I also have negative velocity, so I'm making my way further this way. But I'm making my way further this way at a slower and slower rate, because you can see this area is going up in magnitude by less and less as the triangle completes. By symmetry of the previous ones, I know that this area here is 8. So I have to make my way up by a value of 8. Sorry, I have to make my way down by a value of 8. If I'm below the line, I'm still moving this way. I'm just moving slower and slower. So I'm going to start out as steep as this, but it's going to level off. And the displacement from 16 is a displacement of 8. So it's got to go to 24. So by the time I get here, I am at negative 24. So that's just above negative 25. Now again, it starts off steep, but then it levels off. So the total area under my curve up until now is negative 24. I've got 8 minus 16 minus another 8 gives me negative 24. From here to here, my velocity is 0. If my velocity is 0, what that means is quite simply I am not moving. So my position from my initial position stays constant. In other words, the displacement from the original position does not change, so I've got a flat line here. So this flat line corresponds to a flat line where our position does not change. This flat line does not correspond to a flat line, it corresponds to a slanted line, because here we don't have 0 velocity. Here our position is changing. Here our position is not changing. Now we make our way up. Again, this is 4 by 4, and it's half of that, so our area here is 8. So I'm going to make my way up by an amount of 8. So I'm going to get from negative 24 back up to negative 16. And not in a straight line. Initially, I'm going up slowly. I'm only adding a little bit of area, and then I'm adding more and I'm adding more. See how each step over, I'm adding a greater amount of area? So that's going to start shallow and get steep as I make my way there. It's a segment of a parabola, actually. And now I have constant velocity. And with constant velocity, my position is going to change at a constant rate. So I'm going to have another straight line here. How much is my position going to change? Well, this is going over 4. And my time interval is 7. So I'm going to go up by an amount of 28. I'm at minus 16. So that's going to move me up to, I believe it's 12. Yeah. So I'm going to move forward 12 from minus 16 by the time I get here. So that's 5, that's 10, and so 12 is about there. Okay, so let me recap. At every point on this graph, the height of our displacement time graph is equal to the total area under the curve of the velocity time graph, right up to that point. When the area is above the line, our motion is forward. When the area is below the axis, below the line, our motion is backward. Right here we have an area of 8. Here we have an area of minus 8. The total area is 0. Our total displacement is 0. Here we have a constant velocity of negative 4. We've got an area of 16. So over that time interval, we've made our way a displacement of 16. And because all that's below the line, we're making our way back. Here our velocity is increasing, its magnitude is decreasing. We have negative area, so we're still getting farther away from the line. Here our velocity is 0, so we're not moving. Here our velocity is increasing. We're moving forward, and we're moving forward faster and faster and faster. That's characterized by our shape here. And again, the height we get to, we can calculate by the area. I've got an area of 8, so I've moved up by 8. And here I have an area of 28, so I've moved up by 28. And that's how you get a displacement time graph from a velocity time graph. Now getting acceleration is dead easy. Acceleration is, well, we're at 12 minutes, so I'm going to put it on the next video.